what I will be presenting is a paper that we got accepted at ICML last year, which is called Finding NEM-U, which is about explainable AI for representation learning. So I will start by talking a little bit about some terminology just to get everybody on board to ensure that we understand what we're talking about. Then, of course, some motivation for what we're doing, methodology, experimental results, and then some discussion and future work. So anyway, very briefly, because I didn't really know what level I had to go on, I'll start very low level and just quickly mention what explainable AI or SAI is about. And it is fundamentally a big field that's trying to understand how models work and what models know and what models don't know. But in this work, we focus very specifically on the relations between input and output. So in other words, what part of the input creates the response in the model we're interested in. So if you look down at the three images, you can see that we have two models trying to explain two explainability methods trying to explain why a classifier gets a certain score for the image on the left. So now that we talk about that, then there's the question of supervised learning contra representation learning. Just in our case, when you talk about supervised learning, or well, that's usually when you have like an input signal and output signal, you seek your model to actually learn the moving from one to the other. Meaning, for example, you have a classifier that tells you what a cat is, basically, whether it's a cat or a dog on the image. The other, when we talk about representation learning in this case, it is more, it's basically unsupervised learning. We're trying to learn some representation of our input space. So that could be, we have a lot of images we don't know where from, and we're trying to find a way to cluster them in latent space. We will focus on, in this specific work, we are focused on representation learning, which is a little bit new field. So another thing that's important to quickly out of the way is the difference between occlusion-based explanations and gradient-based explanations. So when we generate an explanation, for example, a classifier, two major fields or way of doing this is either using the gradients of the model or occluding the input image somehow and checking how you get an output response. So if you look down at the two images to your left, you can see one of them are looking at finding all the gradients of the image and using that to explain it. And if you look to the middle one, you can see it has actually occluded part of the image and it will still get the same output response, meaning that this is still a house. So that's the difference between occlusion-based and gradient-based explanations. Finally, for this specific paper, it makes sense to distinguish between what we call feature set explanations and additive feature explanations. So in feature set explanations, we simply say we find a set of features, a part of the image in this case, which combined give the output, but it doesn't tell you anything about which part of this set is most important. Whereas in additive feature explanations, you have every single pixel and you rank them and say, this pixel is more important than these pixels with respect to creating the output of the model. So especially with vision models, we can see that some of these feature set explanations are actually fairly good compared to some of these additive feature explanations because of the way that vision models work. But that is mainly seen in, if we look at supervised explainability for vision models, a lot of these feature set explanations usually are more faithful, meaning that they explain the model in somewhat better. That was a lot of terminology. Let's actually get into what I'm going to be talking about. So to understand what I want to be talking about, we wanted to look into the representation explainability. So basically explaining what part of an input that gives that creates the final representation generated by a model. And in this field, especially when I started this presentation, it is a fairly new field, meaning there's not that many methods, but it's growing fairly rapidly. When we started this, there was mainly two methods that was of note, and we're also comparing against in this work, which is Relax, is the one made by Christopher and Robert and some other people, and something called label-free explainability. So very briefly, Relax, I will come back to that, but very briefly we can say that Relax is creates fairly good explanations, but it is kind of slow because, and we will go back to that, it has to mask out the image. Whereas the other method was something called label-free explainability, which is basically trying to use some of these gradient methods, but make a new target it can actually focus on. The reason why I'm not getting that much into it is because, as you will see from our results, this approach generally creates suboptimal results. So let's go a little bit more into the one that makes sense to talk about a little bit more, which is Relax. So Relax was created by Christopher and some other people and submitted. And the whole idea is to understand this representation model. What we do is we take the input image and we randomly mask out parts of the input image, and we send that through the network and see how far it moves in representation space. Fundamentally, the idea is that if there's something important in the image, when that is masked, that will move the input fairly far away from the original image. So if you look at this bird here, you can see in the case where we mask out parts of the bird that is none of this image. If we assume we have a model where the bird is important, then if we mask out areas of the input that doesn't contain the bird, it will not move the bird that much. But whereas if we mask out the bird, then it will move a lot. So we do this many times, randomly masking the image, and then in the end we can kind of see, okay, which part when we mask that will have moved the representation a lot, and that will give us this heat map that tells us, the areas of the bird is what is most important. So there was kind of the starting point when I got into this project, and this method works really well. The problem with it is we're doing this we're doing this masking randomly. So our question was, can we somehow create these masks in another way? So finally, some key insights to explain this work. We have the first of all, we know from Relax that using occlusion-based psi methods works fairly well for representation learning. That's at least what Relax indicates. So it makes sense to create a method that does occlusion to measure the importance of these representation learning systems. Then the other problem, of course, is that the occlusion-based methods are generally slow, and that is because, on average, most occlusion-based methods take for one input image, and then they run the optimization process. For example, with Relax, we randomly mask that specific image. But that means if you want to run many different images, then you have to do the optimization process for each single one. That means it's fairly slow, especially in large throughput systems. So the last thing we kind of realized was, one, that of course optimization is slow, but prediction is fast. So if we can somehow predict the mask instead of actually optimizing for every input, we should be able to, at least in the inference setting, do it fast. And the other thing is, that was a little bit more interesting, was that we realized that feature set occlusion psi basically can be cast as binary semantic segmentation. So what does that mean? It means that what we're actually trying to do when we have a feature set explanation, especially with occlusion, we're trying to find parts of the input that is important and parts of the input that is not important. That means that technically we can cast it as segmenting the image into areas of importance and areas of unimportance. So finally, we can get to what we actually did. We have these 4 things. So what did we do? We created something we call the neural explanation mask framework. Our goal is to segment input images into areas of interest and areas of non-interest. So first of all, we have the model we want to understand, which is the frozen model. This model is not optimized during training. And then we have the model that will then generate the masks, the model that will allow us to, given an input, predict a new mask. So as you can see here, what we realized when we did this is that it's actually possible to train a model to mask the input of another model. So basically, as you can see here, when we're in the inference setting, we basically send the input to the frozen model and to the masking model, and then the masking network will output some masks, and the frozen model will output the representation. But in the training setting, what we do is we once again we send the input to the masking network, and that will generate a mask. We can then add onto the frozen image. Then we create a masked input image. Then we send both the masked input image and the normal image through this frozen model. And then we get like the representation of the original image and the representation of the masked image. Both of these then go into the loss, and then we optimize to make sure that they're close. And then we also make sure that the mask is maximally small. Basically, we want the smallest area that still yields a representation that is close to the original representation. So as you can see, this can actually be trained. The other thing is we realized fairly quickly that just training a separate masking network from the frozen model was actually really hard to train. So what we found out instead, which turned out to be fairly well, was to extract some input representations of the original image and send them also to the masking network. So instead of having two separate models, we kind of connect the frozen model and the masking network into one self-explained system. So this is kind of the overall neural explanation masking framework. So what does the loss function for this look like? When we look here, we want some loss function that when we optimize, we get a good masking, like the masks should tell something. So there are three things we want. Good. Of course, we want to mask the input, and then we calculate the distance between the representation of the masked input and the original, and then we minimize the distance while maximizing sparsity. In other words, the mask that comes out of this system, we want them to ensure that when we put the mask on top of the input image, then the representation and the mask representation are still close, while still having a fairly sparse mask. So once again, imagine you have that bird. We would just want to get a mask where we only have the bird left and everything else has been removed. And how do we do that? Fairly simple. The loss function simply trades off these two things. It trades off this. So this will be our masking network. So basically, this will be the output of our masking network. So we want a sparse mask. And we also want the distance, which is defined as PD here, between the X and the masked input to be fairly close. There's one more thing we will get back to, and that is this B term here we also had to add, and that is because to make sure that this system is optimized, our mask had to be continuous. We couldn't say this pixel is masked or non-masked because we wanted the gradient to pass through it. But the issue with that is then that means that this it allows us for some situations where this mask is not, where some pixels are fully masked out, and it can kind of cheat the NEM framework. I will come back to that a little bit later. But that is basically, that kind of leaves us with this loss function here. We have a term that ensures that the masked and unmasked image are close in representation space. We have another term ensuring that the mask generated should be sparse, so we want the smallest explanation of the input image. And then, of course, we will have this regularization term ensuring sparse, like binary masking, at least encouraging it. But once again, I will try to explain this B term a little bit later because it's a little bit more confusing than the other things. So after we, as I talked about here, we had the frozen model and the masking network, and we needed some way to combine them in a smart way. And since what we are actually doing is basically segmentation, we realized that taking some ideas from the segmentation literature, namely the UNet, would allow us to have a meaningful way to structure the relationship between the frozen network and the masking network. So basically what we do is that we see the frozen model and the masking network as the encoder and the decoder of the UNet. In other words, you can imagine that this will be some representation generating system. Then we find some different layers of it, and we extract its embeddings of when we give the input image, and we extract the different embeddings and send them of various levels back to our decoder, our masking network. After we did this, we could see that the masking we got was much better. So it seems like when there was no connections between these two things, the results were very subpar. But when we connected them, we started to see really strong masking. And that might be because of the gradients, but we don't really know why yet. So it's important to remember that we don't train the frozen network. The frozen network is solid through all this. Everything that is actually trained is just the masking network. So while we still extract the embeddings, these will be, well, two different runs of the same input image will still yield the same embeddings coming here into here. Of course, the only limitation of that is that now we need to actually, when we want to implement a NEM-U system, we need to find some layers we think we want to extract embeddings from. So, okay, that was kind of the theoretical methodological part. Now we have to talk a little bit about experimental setup. I will try to go through this fairly rapidly, but this will explain how we actually evaluated this. Okay, so first of all, in this specific work, we focused on computer vision models. So we will only be talking about, we didn't do any texts, we didn't do anything except for images, basically. So to evaluate the NEM framework and the NEM-U architecture, we needed some things we need to specify. We need the loss function. We defined a loss function before, but we need to find the hyperparameters, the distance measure we use, the binary regularization, etc. And of course, we need some models and data to actually test our system on, some other methods to compare against, and some metrics we then use to compare the different methods against each other. fairly quickly. First of all, I think this is the most important part, the implemented loss function. For the distance between the masked representation and non-masked representation, we used negative cosine similarity. This was simply because that was what worked for relax. So we decided to do the same thing. For our lambda parameters, we chose 1.5 and 1. That was mainly from looking at the mask, but we found after in an ablation study that these lambda terms, at least the loss function, is fairly robust towards these lambda terms. Then, of course, the occlusion method. Some people would use noise. Some people would use like using some blurring. But in our case, we just did input scaling, meaning that when the masking goes up, that means we just remove the pixel and go towards the gray image. Now comes the little bit interesting part, which is the B term, which is, once again, the B term is the way we ensure that we get binary, or like encourage that we get binary masks. So why did we need the B again? So imagine you have some edge detection model we want to explain, basically, or some model that only looks at edges. So basically in our current loss formulation, if this one would give us, this would be the masking of the image because we scale the pixel down, so it would become a very low, like very high masking ratio. But for the actual images, it's just the same image but darkened. That's an issue because then the explanation, like the model would see these two images at the same thing, but our masking ratio would still be very much down, and then the final explanation would just be everything is important. In another way to actually say this in a little bit simpler way is just when the NEM-U system gives us the non-darkened and the non-darkened and the darkened image, we give it to the explained model. They say they're the same picture, but we have also very heavily masked the entire picture. But once again, the final explanation would just be like saying every single pixel is important because we have darkened every single pixel. So we need to find a way to ensure that it actually flips all the way to 0. So what we do here is basically we set it with a heuristic. And the whole idea is to ensure that the masked image and the inverse masked image, so when we apply the mask and then we take the opposite of the mask, those two representations should be far apart. If we look at this image with the fish again, then what we're saying is like, if I mask out this pixel here, then the inverse image would mean that in that image, it will not be masked out. And then we say they have to be far apart. And to ensure that, if you have a model where it can actually look at the darkened image, then it still has to completely mask out the image. And that is basically the heuristic we use here to set it. We also make sure to scale the negative distance between these images, the masked image and the inverse masked image. We scale that with the positive distance between the masked image and the original image, but that's simply because we only care about binary mask when we already have a fairly good solution. This was a heuristic. It's something I'm not completely satisfied with, but it is what worked in the paper. So the final implemented loss function looks like this. Once again, we have we have a term that encourages this closeness between the masked image and the original image. We have another term that ensures that the masked image and the inverse masked image are far apart. That's why there's a minus here. And then once again, we have the sparsity term here, where we say we want masks that are very sparse. We want small explanations. So that's our final loss function. Then, of course, what did we test it on? We tested it on, well, basically two different architectures, a vision transformer trained with the Dino approach and a ResNet structure trained with supervised classification, SWAP, and SimClear methods. And they're all pre-trained on ImageNet. And then, of course, in the data sets, we used VOC and COCO. What did we compare against? Well, because we know Relax are good, we compared against Relax and its variant called uRelax. And then, of course, the other system I very briefly mentioned, the label-free Psi method, where we used it to, basically what it allows you to do is take supervised methods, explainability methods, and use them in an unsupervised case. Once again, when you see the results, you will understand why I didn't care too much for this, because I didn't talk about it too much, because the results were not really that great. So metrics, generally we measured 4 metrics. Speed, because we want to create a fast version of Relax, so we have to measure speed, which is just how long does it how much time does it take to process X samples. Then, of course, there is locality and complexity. Basically, locality is we have bounding boxes for all our images saying what are important, like what is, according to humans, important areas of interest. So for example, you can see, let's see here, there's something wrong here, this should be low locality, but basically imagine there is a bounding box around this fish, then of course an explanation that is around the fish will have a high locality, but an explanation that is not on the fish will have a low locality. And complexity is just how sparse the mask is. So if you have high complexity, that means the explanation is very big, and if you have low complexity, the explanation is very small. And you want small explanations because it's easier for humans to interpret. So the ideal explanation should look something like this. Now, it should be noted that locality especially is a little bit of a weird thing, because what we're essentially saying is we want the explanation to be what we as humans expected, but that doesn't necessarily mean that's what the models actually use. So in some way, locality is a little bit biased. The reason why we did this is because there's not really any, at the time of our paper, writing our paper, there wasn't really any good ways to measure faithfulness, which is the fourth category. I will get back to that further. We did some things with faithfulness for our paper, but I will explain that a little bit more in depth. But right now, it's just, remember we measured the complexity and locality, which basically tells you, is the explanation where humans expected it to be, and is the explanation small? Okay, so now we have a lot of results. I will go through them fairly quickly. First of all, we are approximately 1,000 times faster than relax during inference. We're actually faster than saliency. That's because, saliency need a forward pass and a backward path. A model just need a forward pass through the original model, and then a forward path through, through the masking network. And the masking network is always smaller than the original network. So that means that, of course, a forward pass and a smaller forward pass is generally faster than a forward pass and a backward pass. And we're about 1,000 times faster than relax, because it has to do this optimization procedure over each image. To understand the speed, it should also be noted that we are only measuring in inference setting. Of course, there is a price according to this, which is we need to train the NEM-U system compared to all the other methods. So if you only wanted one image, sometimes relax would probably be better to do than compared to NEM-U, for example. Locality, we are best in relevancy mass. Relevancy mass is just how much of the explanation that is inside the bounding box, whereas relevancy rank is every single pixel ranked correctly according to the bounding box. And we can kind of see that we have a good relevancy mass, but we have second or third best in relevancy rank. And very simply, that's because if you compare our NEM-U explanations, which are here, and the relaxed one that is here, you can see that we still generate some artifacts here. The interesting questions, of course, is, are these artifacts important to the model, or is these artifacts because our network is not fully trained? So whereas you can see most of our relevancy mass is just directly on the object, and then a small bit in the artifacts, whereas you can see relaxed is a little bit more blurred out, which probably explains why it's a little bit lower in relevancy mass, but it's still better in relevancy rank. And once again, as I said before, with the integrated, like the label-free explainability systems, all the three explanations are, at least in our experiments, quite subpar. Complexity, we have the lowest complexity, like the smallest mask in 3 out of 4 cases. And some of the time is U-relax. And it's basically because we have more binary mask compared to some of the other ones. You can see our mask goes like this. It's almost completely binary. And the other ones are much more, once again, much more blurred out. And that's also the case for the U-relax, whereas you basically threshold relax. Now, one of the reasons why we probably didn't get the best complexity for all models is that we use the same hyperparameter for our losses. And it should be said that for the Dino model, we can probably have turned the masking ratio, like the hyperparameter for encouraging denser mask, we can turn that higher up. We can see from the result afterwards. So, faithfulness, and this is the thing that's most interesting. Once again, we couldn't find any good faithfulness measures while we made the paper. And faithfulness, so to first of all probably explain what faithfulness is. Faithfulness is if you take an image, just to give an example here, the idea of faithfulness is to test if I remove the what is the relation between the actual output of the model and the mask we give. In other words, if I remove the least important pixels according to this mask, I should see a less impact on the representation or output of the model compared to the more important things. So we just check whether these two, whether the relevancy given by the mask, the explanation, is correct according to the output of the model. So we did two things because we didn't have anything for the unsupervised or the representation case. One is that we explained the classifier, the ResNet classifier, and we explained that on data from ImageNet. And then we used that explanation from the last hidden layer, and we used that as an explanation for the overall classifier. Whereas most models will actually explain the output, we explained the last hidden layer basically. And in this case, we can see that we got the highest faithfulness score compared to Relax and some of the other ones. The problem, of course, is that we're measuring this on the last hidden layer and not the output. So the results are probably biased, meaning that some of these methods, if we use them on the output, the actual output layer, it might have given them better faithfulness results. The other way to do it is basically to do something called accuracy over complexity. That just means that we, if you look at our method, it's very binary. So it's actually kind of easy for us to say, okay, we just take this area and see if we just use this area, how close are we to the original image? And then we divide it by how many pixels what ratio of the image we still use. So it's just like, we want to be close and we want the complexity to be low. And in this case, we can see that we tie with uRelax. So sometimes they're better and sometimes we are better. And the problem with this one, let's be very honest. First of all, this measurement is only suitable for some methods where it actually gives somewhat binary masks which have a notion of a threshold. The other big problem is that it's highly dependent on how low complexity is. You can see generally the one who wins are the one who has the lowest complexity in general. Okay, so that was all this. Final thing to talk about. What are some of the issues of the current NEM-U framework, and what could be some ways to mitigate that in the future? One of the things we found fairly quickly after creating this paper is that NEM-U tends to create very cautious masking. So as you can see here, all of these methods, even these, which are kind of bad, all say that the cat is most important. Whereas if our method says that both the humans and the people are important, and this is probably because we are optimizing over a range of images. We don't get one image and optimize that. We train our masking networks on a corpus of data. And that means that if it sees, in some images, the humans were probably most important. In some images, the cat was probably most important. But that means that in some cases, we will get over-cautious, as you can see here. Some ways to handle this in the future will probably be to try to prune out the mask after we generated that, but that will be at the cost of lower inference speed. Then there is some of my personal pet peeves, which is one, the models still need to be tuned. We have tried it on some other data sets, and we found that we had to find some vastly other hyperparameters to make this work compared to the ones we use in this study. Maybe we can automatically discover those though. And then, of course, a little bit more philosophical pet peeve. I think sometimes the explanation is a little bit untransparent, meaning that we have this trade-off between masking and being close in latent space and unbinary masks. And these hyperparameters then define some sort of equilibrium between these things. But a user looking at this mask don't really know, okay, is it this big because it's is it focused too much on complexity, or is it this big because it focuses a little bit too much on accuracy? So there is something with the hyperparameters creating this solution a little bit confusing. So this was my talk about the NEM framework and the NEM-U architecture. And once again, our results show that we get good locality and faithfulness with low complexity at very high speed compared to other methods. And then, of course, we should look into how to prune the masks and try the NEM frameworks on other different modalities. We have actually started doing that. And then right now we use a UNet for images, but maybe if we take the NEM approach to text, we might need another architecture to get better results. So yes, I just want to say thank you to my supervisors and to my collaborators, basically Christian Eagle, Jon Sporing-Polat from Copenhagen University, and Christoffer and Robert Jensen from the Arctic University of Norway. And thank you for taking your time to listen to my presentation.